Welcome to the deep dive. Today, we're not just scratching the surface, we're really getting into the weeds of cybersecurity. We want to pull out those key bits of knowledge you really need.
Exactly. And we're doing it using, well, a set of practice questions from the CompTIA CAS-005 exam. But, this isn't just test prep.
Right. It's about the underlying principles.
Precisely. These questions, they kind of mirror the real stuff security pros deal with every day. Think of it as getting to the core ideas faster.
Our aim here is to give you practical insights, stuff you can actually use to, better protect systems and data.
Yeah.
We'll try to break down the jargon, explain the why behind things.
Yeah, we'll cover a range of topics, from dealing with attacks to securing cloud setups.
Okay, let's jump into the first one.
Right. So picture this. An analyst is looking through logs after a DDoS attack. They see a huge number of SYN packets hitting the server.
Okay.
But here's the key. No corresponding ACK packets. The handshake isn't finishing. So the question is, what kind of attack are we seeing? Amplification, SYN flood, smurf, or man in the middle?
And that points pretty clearly to a SYN flood. Now, for those of us maybe not fluent in TCP handshakes, what's actually happening there? What's the attacker doing?
Well, fundamentally, a SYN flood exploits how computers normally start a connection. Usually, computer A sends a SYN, B sends SYN ACK, A sends ACK. Connection made.
The three-way handshake, right?
Exactly. But in a SYN flood, the attacker just sends tons of those initial SYNs. But they never send the final ACK. Or they spoof the source address so the SYN ACK goes somewhere else entirely.
So the server is just left hanging, holding resources open for connections that will never actually happen.
That's it. It allocates resources for each SYN, expecting an ACK. When it gets flooded with these incomplete requests, it runs out of resources. Legitimate users can't get through.
And I guess attackers use botnets to make this even worse.
Oh, absolutely. That amplifies the scale massively, making it harder to block. It's a constant battle, really. And this is just one type of network-based denial of service attack, right? They all aim to disrupt things. Understanding the different flavors is key to defending against them.
Okay, let's switch gears. Scenario 2. Protecting data. Really sensitive stuff. An organization needs to make sure that even if its database server gets compromised, the crucial data inside stays unreadable. So, what's the most effective method? Tokenization, data masking, full disk encryption, or field-level encryption?
The best bet here for this specific scenario is field-level encryption.
Field level. We hear a lot about encryption generally. Why is encrypting specific fields better than, say, encrypting the whole disk if the server itself is compromised?
Good question. Field-level encryption is really targeted. Instead of scrambling everything, you encrypt just the specific database fields holding the sensitive info. Think social security numbers, credit card details, that kind of thing.
Okay, but full disk encryption protects everything on the drive, doesn't it?
It does when the system is off or the disk is removed.
Yeah.
But if the server is running when the attacker gets in, the operating system has already unlocked the disk. The data might be accessible in memory or through database queries.
I see. So the system's running, the disk is decrypted, but the fields themselves are still scrambled.
Exactly. The attacker gets access to the database files, maybe even runs queries. But the really sensitive columns just return encrypted gibberish without the specific field decryption keys. Tokenization and masking are useful for reducing risk in some contexts, like testing, but they don't offer the same cryptographic strength if the raw database is accessed.
So it's about layers, choosing the right tool for the specific threat.
Precisely. Defense in depth. You wouldn't rely only on field-level encryption, but in this scenario of a compromised running server, it adds a crucial layer for the most sensitive data.
Okay, next up, cloud access. Number 3. A cloud security architect needs a way for users to securely access multiple cloud services, but wants identity management centralized. What should they recommend? SAML with SSO, RBAC with local accounts, Kerberos, or LDAP?
The standard recommendation here is SAML with SSO.
SAML, SSO, lots of acronyms. Can you unpack those a bit? Why are they the go-to for this?
Sure. SAML Security Assertion Markup Language is basically a standard language for exchanging authentication and authorization information. It works between an identity provider or IDP.
That's the central place you log in.
Right, that's your single source of truth for identity. And then you have the service providers, or SPs. Those are the cloud services you want to access. SSO, single sign-on, is the experience. You log in once to the IDP.
And then SAML handles telling all the other services, hey, this person is legit.
Exactly. The IDP issues a secure SAML assertion, like a digital passport stamp saying you're authenticated. The SPs trust that assertion and let you in without needing separate logins. You often see things like OFAUth 2.0 and OpenID Connect used alongside or instead of SAML 2, especially for modern apps. They achieve similar goals.
So it avoids having dozens of separate passwords and accounts everywhere.
It simplifies things massively for users and admins. Trying to manage local accounts on every single cloud platform, that's just asking for trouble. Inconsistent policies, forgotten accounts, security holes. This whole concept is called identity federation. It's fundamental for managing access securely in today's multi-cloud world.
Makes sense. All right, question 4 dives into containers. A vulnerability is found in the base image used for a container running in production. What's the best fix? Options: patch the host OS, rebuild the container with an updated base image, reboot the orchestrator, or sandbox the container.
The correct approach here is definitely to rebuild the container image with an updated base image.
Why not just patch the host OS? Don't containers rely on the host?
They do rely on the host kernel, but the vulnerability here is in the base image. That's the foundational layer of the container itself, the operating system, files, libraries, software inside the container. Patching the host OS is important for host security, but it doesn't change the vulnerable code packaged within the container image.
So the vulnerability is inside the container's own little world, so to speak.
Exactly. Rebooting the orchestrator or sandboxing might contain the issue temporarily, but they don't fix the root cause. You need to go back to the source, update that base image with the security patch, and then rebuild your application container on top of that fixed base.
So it's about fixing the supply chain, essentially.
That's a great way to put it. Container security, application security. It really highlights the need to manage that software supply chain, starting with those base images. Keep them batched.
Okay, question 5 gets into core security principles. An organization wants to make sure users can't deny doing something in a financial app. Like they can't say, I didn't make that transfer. Which principle is key? Availability, non-repudiation, integrity, or confidentiality?
The principle we're looking for here is non-repudiation.
Non-repudiation. Sounds important, especially for finance. What does it mean in practice?
It means you have proof, undeniable proof that a specific user performed a specific action and they can't later deny it. Think about financial transactions. You need absolute certainty about who did what and when for audits, for accountability.
Right, you need to prevent the "it wasn't me" defense. How do systems actually achieve this?
Several ways. Digital signatures are a big one. They cryptographically link a user to an action and verify the data hasn't been tampered with. Secure, detailed audit logs are also crucial, recording every action in a way that can't be altered. It fits alongside confidentiality, integrity, and availability, the CIA triad, as a really fundamental security goal, especially where trust and proof are critical.
Got it. Okay, number 6, back to access control design. A security engineer needs controls for a financial system. The goal: employees should only access information strictly necessary for their job. Principle of least privilege, right? Which model works best? Bell Lapidula, DTAC, RBAC, or MACAR?
For that requirement, role-based access control, RBAC, is generally the best fit.
RBAC again, we saw with cloud. Why is it so good for this kind of internal system applying least privilege?
Because RBAC links permissions directly to job roles. You define roles like teller, loan officer, auditor, and assign permissions to those roles. Then you just assign users to the appropriate role. A teller gets teller permissions, nothing more. It naturally enforces least privilege.
As opposed to the other models, like DTA.
Well, discretionary access control, DTA, lets resource owners decide access. That can get messy and inconsistent in a structured environment like a bank. Mandatory access control, NACI, is very strict, often based on security labels like confidential or secret. It's powerful but can be complex and inflexible for typical business workflows. RBAC usually hits that sweet spot, structured, manageable, enforces least privilege effectively for most organizations.
Okay, question 7. A common audit finding: data moving between departments isn't encrypted. Oops, what should be implemented? DLP, data in transit encryption, EDR, or secure boot?
The direct fix here is data in transit encryption.
Seems straightforward. Encrypt the data while it's moving. Why wouldn't something like DLP work?
DLP, data loss prevention, is more about preventing sensitive data from leaving authorized locations or channels. It might flag unencrypted sensitive data, but its primary job isn't encrypting internal traffic. EDR is about endpoint threats. Secure boot protects startup. They don't address data moving across the network.
So you need to protect data in its different states.
Exactly. Data at rest, on disk, data in use in memory, and data in transit on the network. Each needs specific controls. For data moving across the wire, encryption like TLS or IPsec is the answer.
Right, protect it while it travels. Okay, number 8, into DevSecOps territory. The team wants to stop developers accidentally committing secrets, API keys, passwords into the code repository. Big problem. Best way. Encrypted environment variables, restrict repo access, pre-commit hook with secret scanning, or store secrets in config files.
The most proactive way to prevent this is the pre-commit hook with secret scanning.
Pre-commit hook, how does that work? Is it like an automatic check?
Yeah, essentially. Git hooks let you run scripts automatically at certain points in the workflow. A pre-commit hook runs before the code is actually committed. You integrate a tool that scans the code changes for patterns that look like secrets, high entropy strings, keywords like a pikey, etc.
And if it finds something?
It blocks the commit. It prevents the secret from ever even entering the local repository history, let alone getting pushed upstream.
That's clever. Better than finding it later. What about the other options?
Using environment variables is good practice for using secrets, not checking them into code. Restricting access helps, but doesn't stop someone with access from making a mistake. Storing secrets in config files can also be risky if not managed perfectly. The pre-commit hook really embodies that shift-left idea, catch the problem as early as possible in the development cycle.
Makes perfect sense. Okay, question 9 is about planning. A security manager is running a tabletop exercise for a ransomware incident. What's the main goal? Evaluate financial impact, test endpoint protection, identify gaps in the incident response plan, or validate backups.
The primary goal of a tabletop exercise like this is to identify gaps in the incident response plan.
So it's less about the tech and more about the process and people.
Exactly. Tabletops are discussion-based. You walk through the scenario, okay, ransomware is detected on these systems, what do we do now? People discuss their roles, the steps in the plan, communication flows. The aim is to find where the plan is unclear, where steps are missing, where communication breaks down before a real attack hits.
So things like testing endpoint software or checking backups would be done differently.
Yeah, those involve technical testing, different kinds of drills or validations. The tabletop is purely about testing the plan and the team's understanding of it. Evaluating financial impact might be part of the outcome of a real incident analysis, but it's not the goal of the exercise itself.
Got it. Focus on the plan. Okay, last question, number 10. Back to the cloud and protecting valuable data. An organization has intellectual property it wants to analyze in the cloud, but needs to keep it super secure, yet usable for analytics. Best method. Symmetric encryption, homomorphic encryption, one-time pad, or data masking.
The best fit for that specific, rather advanced requirement is homomorphic encryption.
Homomorphic encryption, that sounds complex. What's special about it? How does it let you analyze encrypted data?
It is pretty advanced. It's a type of encryption that allows certain computations, like statistical analysis, machine learning tasks, to be performed directly on the ciphertext, the encrypted data. So you can send your encrypted IP to a cloud analytics platform. They can run calculations on it and send you back an encrypted result.
Without ever decrypting the original data.
Without ever decrypting it. Only the owner with the key can decrypt the final result. It keeps the data confidential even while it's being processed by a third party or in an untrusted environment.
Wow, so you get the analytics benefits without exposing the raw IP.
That's the promise. Now, it's still computationally intensive and not practical for all types of analysis yet, but for specific use cases involving highly sensitive data in the cloud, it's a very powerful concept. Symmetric encryption requires decryption first. One-time pads are theoretically perfect but impractical. Data masking changes the data, which might skew analysis. Homomorphic offers that unique ability to compute on encrypted data.
Okay, that's a fascinating glimpse into more advanced crypto. So maybe a final thought for everyone listening. As you think about these different areas, DDoS, encryption, access control, incident response, secure development, which one feels like the biggest challenge or maybe the murkiest area in your own work or understanding?
Yeah, maybe it's securing containers, or perhaps it's getting a handle on cloud identity federation, or even something seemingly basic like non-repudiation.
Because even the concepts that seem simple on the surface often have a lot of depth, and they're constantly evolving as threats change. So keep asking questions, keep digging deeper into those areas that feel challenging. That curiosity is really key in this field.